we're back. So in our previous examples, we've looked at how we can evaluate limits analytically by sort of applying algebraic shenanigans to get around a problem if we just tried to plug a limiting value directly into the function, where we end up with like a zero denominator, which is, of course, a bad thing. So all the examples, though, have involved polynomials and like rational functions, which are just two polynomials sitting one over top of each other. I wanted to stretch things a bit beyond that. So breaking us in here, this may look a little bit familiar. We had an example where I dealt with this on our calculator, looking at this numerically. So I've swapped out my x variable for an h. One, I like to keep you on your toes. Two, not to spoil things too much for what's coming down the pike, but stuff like this is going to turn up a lot in the future. So anyway, so we've got the limit of the square root of 4 plus h minus 2 over just h. And we want to know what's happening to this thing as we let h get really teeny tiny, shrink down towards 0. So direct sub, you'll probably not be terribly shocked or dismayed that if we plug 0 into this thing, oh no, 0 denominator. Oh, maybe 0 in the numerator, because the square root of 4 is just 2, and 2 minus 2 is 0. All right. So it looks like we should be able to do something. We can dig in on this. And if you recall what we were doing as far as pre-calc is concerned, now is the time that one thing that I had you do that felt really kind of out there, where we made things ugly before they got less ugly, is a factor. So I'm going to go ahead and erase this just so I don't have to do too much rewriting. What we're going to do is rationalize the numerator of this beast. So hopefully you'll recall. So we swap around the subtraction sign in the middle of our top here with plus. Remember, don't touch what's underneath the radical. It's important for what we're going to be doing in a minute. And remember, whatever we do to the top, in order to avoid changing the function, we got to do that down here as well. Okay, so again, this is one of those, but it's uglier now, but it turns out it's really not if we dig in our heels just a bit. All right, so we have the limit as h approaches 0. If we work out what's going on top side on this bad boy, this thing times this thing, the square roots, go bye-bye, and we're left with 4 plus h minus this guy squared. 2 squared is 4. And then down below, we just have this h from up front hovering around out front of the grossness in the back. And hopefully you see where this is going, because 4 minus 4, boom, they're gone. All right, so from there, all we have left in the numerator is now an h, and you can probably already see, oh wait, we also had an h down there. I like to cancel it this way, like on 2 separate lines, just to avoid, people getting crossed up as to what happens. So sometimes I've seen students who will like slash those out, and they slash these out, and they'll get crossed up as to what their operations were, and it throws things off. Anyway, from right here, it's pretty clear. I hope that these guys can go poof anywhere other than when h is equal to 0. Again, that's the key behind this. Limits care about what's happening near 0, not at 0. So we're okay with killing it all. Anyway, now in the interest of board space, I'm not going to like completely rewrite this thing, but all we've got left in the numerator is a 1. And down below, now we can plug in h equals 0 without anything going sideways on us, because the square root of 2, or the square root of 4 is 2, and 2 plus 2 is no longer 0, it's just 4. So direct sub at that stage gives us a limiting value of 1/4, which is, kind of nice. All right, so we talked about rationalizing stuff. I'm going to dispense with doing another example where we use this exact same trick, because, we've already done another example like this. So if you want to, phrase it as a limit and see what happens. So what I want to do now is take a look at some functions that, don't look like polynomials, at all. Trigonometry, everybody's favorite. As it turns out, you'll notice I've got a limit here involving a couple of trig functions. We've got a tangent function and a sine function. So we haven't done a ton with trigonometry at this point. I did post sort of a resource, in our previous material on pre-calculus, just kind of trying to remind everybody what the trig functions are and why they matter to us. So kind of going forward, I'm going to take for granted that you're familiar with them in the sense of, functions you can like pop into your calculator. Do remember, radian mode. Don't use degrees. So yeah, deal with it. Anywho, so you may recall looking at that handout of limit properties that so long as an individual trig function is defined, we talk about the domain of the functions in there. We can do that direct sub thing. You can just kind of take this and feed it right in, and it's all well and good. Unfortunately, that doesn't work out for most of the trig functions. The sine and the cosine are pretty well behaved, but the other four, they all have places that they're not defined, which throws a monkey wrench into stuff. And additionally, then we have stuff like this. We have tangent of theta over sine of theta. For what it's worth, do the same old direct substitution thing because that's pretty much everybody's first move here. 0 down below. The sine of 0 is 0. That's bad. You try to do the tangent of 0, you can check in your calculator. I'm not requiring you to memorize any tables of trig values, but yep, you'll get 0 again. So there should be something we can do to unpack this from that 0 over 0 setup. And as it turns out, there is. It's just that we've got to play around with trig identities and definitions and stuff like that. So, and if you need to, go grab that resource file, take a look at it. Some of this stuff is on there. If not, it's okay. Anyway, the real trick to this is the following. This is one of those like kind of key advice deals I'll often give to students. By the way, that's the variable theta. That's what my Greek letter thetas look like. They said I'm trying to keep you on your toes with the symbols here. Anyway, so when all else fails, one of my previous math teachers told me you can always take trig functions and you really only need 2 of them. You really only need the sine function and the cosine function. The other 4 are all just kind of variations on, or combining sines and cosines or doing something with them. As it turns out, in this instance, the tangent of theta can be rewritten like so. So we have sine of theta over cosine of theta. So now we've got this somewhat intimidating looking like triple-decker fraction with a bunch of trig functions flying around in it. So I'll give you a moment to collect yourself if that was kind of freaky. I get it. So we haven't done much trig at this stage, so it's all right. However, now once we accept that they're there, we can just kind of maneuver these around. Remember, dividing by something like this sine of theta is the same thing as multiplying by its reciprocal, 1 over the sine of theta. So we can clean this sucker up as follows. So we'll have all we have in the numerator is sine of theta. Then we'd have this guy times this guy, because now it's like 1 over sine of theta off here on my wall that I can't write off. So we have cosine of theta times sine of theta. And you may recall, oh, look, everywhere other than 0, you get the idea. Sine of theta, they go poof. Now, at this point, if you try to do a direct substitution, all that's left in the numerator is 1. Down here, we have the cosine of 0. If we do a direct substitution, lo and behold, the cosine of 0 is also 1, and 1 over 1 looks awkward. I prefer just writing 1, because it looks less like I just wrote a really big plus sign all close together. All right, so that's one trig limit. I wanted to take a look at another one real quick before we draw this video to a close. So last example for this particular video, you'll notice now I've changed my variable yet again, because like I said, I like to keep you on your toes. So we have up top, we got a trig function, sine of 5t. Down below, there isn't a trig function. That's not a typo on my part. All I wanted down there was 2t. Okay, so we take a look at this guy. Spoilers, direct substitution, 0 over 0, 0 over 0. I should point correctly, right? So something should clean this up. Now the catch is, it's not immediately apparent. No, don't just try to cancel the t's and say that it's sine of 5 over 2. You can't do that. By the same token, we can't really just like yank this 5 out of the trig function. This is like, it's not multiplication or anything like that. So as it turns out, one of the special limits that pops up on that handout of, limit laws and whatnot, references what happens if you've got like limit of sine of x over x. It's not quite what we got here, but maybe we can make this thing right here exactly match that guy down there. All right, so here's my plan. So first off, this 2 is really just constant. I can pull him out from our limit laws from before, like I did with that numerical example. So yank him out front. We got a 1/2 limit. T goes to 0. Sine of 5t over t. All right, now here's the catch. Like I said, we want these two guys here to be an exact match. At the moment, they're not, right? There's a 5 here. There's not a 5 there. Well, we can put a 5 there by multiplying by 5, right? Aha! But if you got a fraction like this, just like we saw with that rationalization thing, if we do something down here, we have to do the same thing up top. All right, so we have 5 sine of 5t. My apologies for the 5 and the s looking alike. That's a problem with my handwriting. Anyway, now don't cancel them right back away. What we're going to do is use that same property that got the 2 out front in the first place. We're going to drag him out. So we have equals 5/2 limit t goes to 0 sine of 5t over 5t. And at this point, technically, we need to adjust this and say, well, as t gets close to 0, 5t also gets close to 0. But by and large, the idea is now we can call in that special limit, sine of a thing over the same thing, as the thing closes in on 0, ends up giving me a limiting value 1. So we have the 5/2 from out front. We've got the 1 that results from all of this stuff right here, according to our special limit. And the overall limit is simply 5/2. Okay, so I wanted to play around with an example of this because it's kind of unusual. I said we haven't done a ton of trig functions. I want to make sure people don't just end up thinking, oh, well, I factor out the 5, I factor out the 2, and then that's kind of what it ends up looking like, but that's not really like the algebraic or trigonometric move you can make. So just be on guard about that. The principle, hopefully this will guide you if anything of this sort comes up. All right, I'm going to have to jump over into like screenshot, screencast mode rather, for the last thing I want to talk about, to examine some ways that limits end up failing to exist.